In this video, I'm going to work multiple examples involving the physics concept of work. So here is example 1. We have a ball rolling across the floor. We are told that it initially has 6 joules of energy and the force of friction is 2 newtons, and we want to know how far did it roll. So as always, pictures are good. Here is the starting position of my ball. It has 6 joules of energy. Here's the ending position. It is not moving. So all the energy has been lost. And if we look at the free body diagram of the ball, we have a normal force from the floor on the ball. We have the ball's weight. And we have friction opposing the motion. The normal and the weight don't do work on the ball because they're perpendicular to the motion, but the friction does. So work equals a change in energy. Change in, remember, is final minus initial. So that is 0 joules minus 6 joules, or a negative 6 joules. But work has another definition. It is a force multiplied by distance. The force in this case is the force of friction, which up above we are told is 2 newtons. Oh, that's a B. There we go. So 2 newtons times the distance equals negative 6 joules, or the distance is 6 joules divided by 2, or negative 3 meters. And remember what the minus sign tells me. It's just telling me that my distance traveled is going to be opposite direction of the force of friction. So if you want to think about it as a plus 3 joules, you can. The other thing you could have thought about is friction does negative work, so this should have had a negative sign in front of it, in which case it would have come out as plus 3 to begin with. That's probably the better way. So we have an object moving across the floor at constant speed. What is the total work on the object? Okay, well, think about the object's free body diagram. I have normal from the floor on the object. I have the weight of the earth on the object. Okay. Constant speed. That tells me no acceleration. No acceleration means the net force has to equal 0. Right now I have no net force because the normal and the weight balance each other, but also the normal and the weight are perpendicular to the motion, so they do no work. They're perpendicular. But you're thinking, this is a floor. There might be friction. But I have to have a net force of 0, which means there has to be something else going on. So maybe it's a force from a child pulling on the toy or something like that. So I'm just going to call it a generic force from a pull on an object. It's something. We're not given enough information to exactly identify if it's a string or if it's a normal force. It's something. Because the net force equals 0, this one and this one have to be equal in length. So while this one adds energy to the system, this one is going to remove it because it's opposite the direction of motion. They're equal forces. It's going in the same distance in both cases. So 0 is the answer there, because the friction and the other force are equal. The distance is equal, and they're in opposite directions, which means one adds energy, one removes energy. For the third example, we have a car accelerating from rest at 3 meters per second squared. So that's giving you the acceleration. We are told the force of the friction on the car is 6 newtons and that it travels like this for 10 meters. So again, I'm going to begin by drawing the free body diagram. I have a normal, I'm going to call it a road on the car. The car has some weight. There has to be something that causes it to accelerate, so I'm going to call it some engines. And I have friction because frictionless roads are considered bad, if you will. We are told the force of friction over here is 6 newtons, so I'm just going to make a note of that. In order to determine how much energy does the car have after going 10 meters, I need to know something about the forces. So to do that, I'm going to look at F net equals ma. I know that this force will add energy, that force will remove energy. So the net force is the force that should matter when I'm looking at how much energy it has total. So F net times d. The mass is 20 kilograms. The acceleration is 3 meters per second squared. So that's 60 newtons. The net force is 60 newtons. D, I'm told, is 10 meters. So the work is 600 joules. I could also ask, though I didn't here, how much work is done by the force of friction? Well, the work due to the friction multiplied by the distance has to be the force of friction, which is 6 newtons times 10 meters, or 60 newtons. If the total is 600 and the friction does 60, that means that the other force here has to make up for that. Total is 600, friction removes 60. That means that FEC, let me try that again. FEC does 660 joules of work. It adds 660, friction removes 60, resulting in 600. For the fourth example, I have a block. It moves across a surface for 3 meters with a 5 Newton frictional force. How much does its energy change? So again, we have a normal from the surface on the block. We have the block's weight. We have friction, and we don't have any other information, so we're going to assume that friction is the only force. So the work is going to be the force of friction times the distance traveled. We're told it's a 5 Newton frictional force, and it travels through 3 meters, so that's 15 joules of work. But it's negative because the friction removes the energy. So the work is actually negative 15 joules, but work equals a change in energy, so the energy change is negative 15 joules. It has lost 15 joules of energy. And for our last example, we have a block moving horizontally for 3 meters. So here it is initially. Here it is final. The distance between those 2 points is 3 meters. And the question is, how much work does gravity do in this process? Remember, gravity points downward. Finishing out my free body diagram.